we're all familiar with the humble envelope. We've used it, for years and years, all our lives. But we really think about all the different ways we use it. So let's start by considering what you'd put into an envelope. The contents of an envelope can be something that is obviously very straightforward, very easy to read, intended to be read by anyone, or at least whoever opens the envelope. This is probably the most straightforward traditional use of an envelope. But you can also use an envelope to carry other kinds of contents, like encrypted contents which are meant for somebody who has a key or some way of decrypting the contents. Envelopes can also be used to hold things like certificates. Certificates warrant that something else is true about something and may carry their own kinds of authentication, signatories, things like that on them. Another thing that you could put inside an envelope is a small piece of data, like a QR code. This is actually an example of a UR request for an output descriptor. We're working on another app right now called Gordian Coordinator, which is a multi-sig partially signed Bitcoin transaction coordinator. And again, it's a reference tool. It's not meant to be a commercial product on its own. It's meant to be something that people study and use and adopt the technologies they're in. So it can be a small piece of data like this, or it can be a large piece of data. There's no reason why you can't put volumes inside an envelope. So now we consider what can be on the inside of an envelope, what can be on the outside of an envelope. Well, typically envelopes are marked with things like who's sending it, who's the recipient, but you can also have other kinds of permits or warrants on it, like the stamp that indicates that you have permission to mail it, or the cancellation mark, which indicates that it was mailed. So there's these kinds of metadata on the outside of the envelope that goes along with whatever happens to be in the contents. Another thing that can be on the outside of an envelope is things that have to do with policy, like who gets to read it, under what circumstances should it be used, things like that, business rules. Another thing you can find on the outside of an envelope are seals, things that can only be that basically authenticate the contents of the envelope and can only be created by certain parties. Envelopes themselves can hide what's inside them. Often when you use a security envelope, you don't want people to see what's inside the envelope unless they open it. This can be carried to any extreme you want, making sure the envelope is opaque to various kinds of inspection. And obviously this corresponds to encryption in our digital space. But envelopes can also be used to selectively reveal parts of information that is inside them. And in some cases, you want to reveal a lot about what's inside it. You want to be very transparent about the contents without actually letting you touch or use it unless you can actually open the envelope. Very often you want to lock an envelope and make sure that only people with certain credentials can get inside the envelope, because whatever inside it is valuable. And another thing we don't think about too often, but we're all familiar with it, is that you can put an envelope inside an envelope. The self-addressed stamped envelope being, a good example. Of course, there's no reason why you couldn't carry this on ad infinitum and put envelopes inside of envelopes inside of envelopes if you really wanted to. And in fact, there might be good reasons to do this under certain circumstances, especially in the digital world. So having kind of done that little survey, there's no reason why you wouldn't want to at times mix and match these things. You might want, for example, an envelope that shows its contents but also carries a seal, or maybe an envelope that shows its contents but carries a lock that can only be opened by certain people. So in other words, you can do a lot with envelopes, ranging from very simple to very complex. And as Alan Kay, a computer scientist I admire, said, simple things should be simple and complex things should be possible. So that's a value we have at Blockchain Commons. We want to make sure that the technologies that we invent with both serve the needs of the community and are things where, like for example, the UR kit that I worked on creating, it's simple to use from an adoption point of view, but it does some pretty sophisticated things under the hood in terms of fountain codes and things like that to be able to transmit larger quantities of data than a single QR code can normally hold. So in terms of all the things I've shown you with envelopes, what kind of data structure could do all this? It would have to be pretty complex, right? Well, let me show it to you. So here it is. This is written in Swift, but it's only slightly abbreviated, but here it is. So an envelope, a crypto envelope, it has a subject and it has a number of assertions about the subject. That's an array of assertions, and that's it. Now, obviously, it's a little bit more complex than that because I haven't explained what a subject or an assertion is, but at a very high level, an envelope looks very simple because it is. So before we go too deeply into that, I want to start with a relevant example of this conversation. I want to show you how you would use this technology right now with running code that we currently have in Swift to use sskr to shard a secret payload of any size and then share it with several parties for later recovery. So I'm going to show you a few lines of code. This will go by pretty quick. It's actually pretty simple code. So let's say we have Dan, who starts by creating a seed, something he wants to protect, and he adds several pieces of metadata to it: a name, a creation date, an arbitrary length note, and this makes it basically exceed the size that sskr by itself can handle. So if he wants to actually shard this, then just a few lines of code will do it. He creates a content key, which is a symmetric key, and then he creates a set of envelopes by first encrypting the contents of that envelope with the content key, and then by splitting, and this is an sskr specification, how many groups, what's the threshold group. So there's it's one group which has 3 shares, 2 of which is the threshold in that group, and then that content key is going to be used to recover the contents. So that's that second line there. The third line is just basically turning the group of envelopes into a flat map into a flat array of envelopes, and then the last line just converts them to URs. URs, as you're probably familiar, look like this. There are a URI, which is, URL is a kind of URI. It begins with UR : and then the type of UR it is. In this case, a crypto envelope. The rest is just text, and it's designed to basically be highly compressible into QR codes. Surprisingly, base64 is not the best way to do that. And then, since we were targeting QR codes very heavily, we invented a system called bytewords to do that. So on the receiving side, we have these 3 envelopes, sent URs 0, 1, and 2, and let's say that they were distributed to Alice, Bob, and Carol. But let's say that Dan only managed to recover the second 2 envelopes, Bob and Carol's envelopes, and that meets the quorum, though. So in that case, he creates an array of the 2 envelopes, and then he recovers the seed. He basically tries to create an envelope with the shares and then extract the seed from that, and that works. Assuming that actually completes and doesn't throw an exception, it was a success. It's that simple. But let's talk about the actual shards themselves, or shares themselves. From a high level point of view, there's 3 of them, obviously, and they're all identical in terms of this one, except the contents of the sskr share, which is different for each one. And all they are is an envelope which has a subject, which is the encrypted message, and then one assertion. The assertion says this is encrypted using sskr, and here's one share. As I mentioned before, here's the envelope again. The subject is the encrypted message, and the assertions each assertion has 2 parts: a predicate and an object. So in this case, the predicate is the lowercase sskr share, and the object is the uppercase sskr share. So it says what this is, and this is one of the sskr shares that this was split with, and here's the sskr share itself. Now you notice that the definition of assertion here, that the predicate and object are themselves envelopes. And in fact, the subject itself, one of the possibilities is for it to be an envelope. So this is where we get the nesting, where we get the envelopes all the way down. But that's not generally, that's for more complex cases. For this simple case, you just have an envelope with, which is, nested 1 level deep. So let's look at the actual CBOR. Now, as you may know, URs are built on top of CBOR, the common binary object representation, which is kind of like JSON, but without the text. It's this binary. And this looks similar to the simplified diagram I showed you earlier. It's an envelope with encrypted message, with 2 envelopes for the subject, for the predicate and the object, one of which says this is just an sskr share, the other is the sskr share. And if we kind of color code this, you can see that the encrypted message, which we've actually documented separately, it's a crypto message. You could create a UR with just a crypto message. It's encrypted using cha-cha poly. And the sskr share, which we also documented in our research paper. So these are pre-existing structures, but they happen to be enclosed in a crypto envelope. Now, as I mentioned, crypto envelope is actually a pretty simple structure, and we have a pretty robust library for constructing envelopes of any complexity. But if you were working on, say, an embedded system and you didn't want to, implement envelope in all its fullness, but you still want to read and write this particular structure, all the gray binary you see is just boilerplate, basically, in that case. And so you can actually just read and write just these bytes, and then just care about reading and writing the encrypted message and the sskr share. And as I mentioned, there's 3 of these in this case, in a 2 of 3. And then you distribute those to the various custodians, gather them back, and then combine them and using the sskr algorithm. And that's the whole scenario right there. So I've really only touched briefly on kind of the high level concept of what crypto envelope is and can do. I want to make it definitely relevant to this conversation. There's a lot more it can do, but you don't need to worry about it if you don't need it. And so that's where I'll leave this. Thank you very much for your attention.